In this module, we're going to talk about diffusion and effusion, what they are and the difference between them, and a little calculation. So first of all, what diffusion is. Diffusion is the mixing of gases. So imagine you have a glass container, two bulbs, with a stopcock separating the two. You have one gas over here and one gas over here. Now, we know about the kinetic molecular theory, and that describes what these gases are doing before and after we open the stopcock. So they're moving in random directions, straight lines, bouncing off each other, all that good stuff. Now when we open up the stopcock, because they're moving in random directions, there's going to be the passage of gas molecules from one side to the other. This mixing is called diffusion. And this will pretty much keep on going until we have about the same number of the red ones on the left and the right, and the same number of the yellow ones on the left and the right. So diffusion is the mixing of gases. An example of this would be opening up a bottle of perfume in the corner of the room. Now, when you open up that bottle, if you're in the opposite corner, you probably won't smell the perfume yet, but eventually you'll smell that perfume. That's because the molecules that give that perfume its odor are vaporizing. They're going from the liquid to the gas phase. Once they become a gas, they do the things that gases do. They move in constant motion, random directions, bouncing off each other, bouncing off the molecules of air. And following that motion, they eventually spread out through the room, and then you smell it. Now, effusion, this is what it is. It's the escape of a gas through a small hole into a vacuum. So the difference is diffusion is the mixing of two gases together. Effusion, one gas is going into a vacuum, where a vacuum means there's no gas there at all. Now, this particular setup here is what we're going to use to do some calculations here. So look at this. This gas over here is doing the things the gas is doing, moving in random directions, straight paths till it bounces off things. Now, because they're moving in, the molecules, the particles of gas are moving in random directions, every now and then one of them hits this hole and it passes through into the other side where there's a vacuum. Now, once molecules start passing through and getting into this side, well, it's no longer a vacuum, but the molecules of gas or the particles of gas are moving in random directions, straight lines, constant motion, and every now and then they might hit that hole and pass back through. But at first anyway, because there are a lot more of the gas particles over here than there are over here, there are more going from the left to the right than there are going from the right to the left. And so you start getting more particles over here and few over here. But all the time, there still are some of them going back the opposite direction, just not as often as they're going from the left to the right. Now, when you get the same number of particles over here on the right as you have on the left, then the same number will be going from left to right as are going from right to left, and the amount or the concentration stays constant, even though individual particles are passing back and forth all the time. Now, let's imagine that we have two different gases over here. Now, let's start out with the hole closed, all right, and the vacuum over here. Just imagine that, okay? Now, let's open up the hole. One of these gases is lighter than the other. They're at the same temperature because they're in the same container. And remember, temperature is proportional to the average kinetic energy. So they have the same average kinetic energy, but remember, kinetic energy is equal to 1/2 mass times velocity squared. And we do the mean square speed. Now, if they have the same kinetic energy, but one of them has a smaller mass than the other, that means the one with the smaller mass must be moving faster on average than the other one is, than the heavier one. Does that make sense? So because they both have the same kinetic energy, let's do it this way. Where 1 represents, say, the light particle, and 2 represents the heavier. They have the same temperature, so they have the same kinetic energy. These are equal to each other, but if mass 1 is less than mass 2, then for these to be equal, u1 squared has to be bigger than u2 squared, right? So that means that the lighter particle is moving faster. Now, because it's moving faster, it's going to just randomly hit this hole more often, and that means the passage of the lighter gas from the left to right will be more rapid than the passage of the heavier gas. Now we have Graham's law of effusion, which describes what we were just talking about. It says when you have two gases in the same container and they start to effuse, as they're effusing, the rate of effusion of one gas divided by the rate of diffusion of the second gas is equal to the square root of the molar mass. The m is the molar mass of the second gas over the molar mass of the first gas. Notice the 1 and 2 are the one's on top, 2 is on the bottom over here, 2 is on top, 1's on the bottom over there. So what's a rate? A rate is how many pass through, say, per second or per minute. So 20 per second pass through, that would be a rate. For example, let's say we have oxygen and an unknown noble gas in the same container and let them effuse. And we find out that oxygen gas effuses 2.03 times as fast as this unknown noble gas. What noble gas is it? Well, we use Graham's law of effusion. The rate of effusion of oxygen over the rate of X, the unknown, okay, is equal to 2.03. That's what this says here. It effuses 2.03 times as fast. That means the rate of oxygen to the rate of X is equal to 2.03. Now that's equal to the square root of the molar mass of the unknown gas divided by the molar mass of oxygen. Now do you guys see where I got this number from? This is the molar mass of O2, oxygen, 2 times 15.999 grams per mole. Now to solve for the molar mass of X, once we know the molar mass of X, then we can just look on the periodic table and see which noble gas it is, right? So what we're going to do is we're going to square both sides. So we squared the 2.03. When we square this side, we get rid of the square root sign. And then we're going to multiply through by 31.998. And we get this right here. Multiplying this out, squaring this, multiplying that by 31.998, I get about 131, 132 grams per mole. The closest noble gas to that is xenon, and our unknown gas is xenon.